ladies and gentlemen, give him a huge round of applause.
डालना पड़ेगा इसमें डालना मसाले very good afternoon, one and all present in the hall, dignitaries and my dear students. See, my topic of the will be of very low nature because I know this has been prepared for you. Any type of difficulty, please come forward immediately. Nothing very high I am going to talk. You know everything. Only thing, how these things which you know is put in the word known as modeling. That's all I have done. Nothing else. You know everything. So please do not hesitate in stopping me anywhere, anytime. See, I have written 2-3 lines here. What it says, what you understand for the model. So this is model. You are making a model. Somebody says you are making a model. What for you are making a model? A model of the car, a model of the helicopter, anything. That way, I am going to synonymize the word modeling. What is the meaning of the modeling? So what I said is, modeling is just miniaturized representation of anything. A small representation, very small representation of anything. A system, it can be a device, it can be a system. Alright? Then we said imitation. You try to imitate me also in the class. After the class, some students of mine try to imitate my words also, my action also. That is also a model. Then we say anything, any item you take. How this consists of, how it has been composed of, what type of model is there. We say one body center, cubic center, say tetrahedron. So what type of representation? One atom looks like this. Then if these atoms make the body, make the system, how does it look like? That will be miniaturized model. System or the postulates of the systems all come in the same way. So what we say, the device behavior can be any device you take. Device is what? You put something, you get something other than what you put in. That depends on the characteristic of the device. Now device is what? So what we say is the device behavior. If I can predict the device behavior, that is what we model. I have a device. The characteristic of the device, something is known to me, and then I can say the device will behave like this. Alright? So it can be in the form of the device we are required. Anything you write. A diode is there, you write something like that. Phenomena is essential for both engineers and the scientists. Any device or any phenomena, unless you model it, it cannot predict all types of behavior. So it is essential for both engineers and science people to know the mathematical model. Or out of the mathematical model, what I enjoy, see, just enjoy this. I go on playing with this mathematical model, I can enjoy it. Yes, I can do this also. I can do this also. What I imagine, Beyond that I can do it. See and enjoy, we also enjoy this. That's what. Then we come to the point, what science says. Science tells you the principles. What engineering does, applies it. What is technology? Technology gives you a tool for these applications. So just as transistor was invented, what engineers did, took the transistor, put it in the form of different types of circuitry, whether for the amplification, whether for the switching, with all types of gadgets. Then technology came. How many transistors you can put in together to manufacture very, very complicated chip in the form they want. That is why we said engineers who are taking the inventions, applying it and using the technology as the tool are innovative. Now, to remain globally, what we are talking about the innovative, to remain globally competitive, what we must do and what we must understand is nothing but art of design. Unless I know the art of design, something happens, I will not be able to change it. So I must know art of design, then I must be able to modify whenever I need it. I must be able to modify it. If I know everything, then only I can modify it. So I must know the art of design. I must be able to modify it. The time comes, some modification I have to include. Yeah, this modification I will include. Then it was just a surprise for them. And then shock for those who had very large inventory. Manufacturing process were on. What will we do in this one? But then it came into reality and we accepted it. It is working very fine. It worked very fine. It is working very fine. So that is what we say. This with the advancement in technology. But we say change in technology for us. I am talking about this environment of Indian university. Change in technology for us is more horizontal. Vertical, horizontal, you understand? Vertical is what? Coming from micro to nano to, say today, 22 nanometer, 16.5 nanometer. That is vertical. But so far we are concerned, it is horizontal. Changes are mostly transformation for us. We are talking about us. Changes for us are mostly transformation from analog world to digital world. You know what is digital world? It's known to you. Very robust against the environmental change. Means against the environment. Very robust system. Digital system is very robust. So for the environmental change. So change is from analog world to digital world or hardware to software. You understand this? Hardware to software. You are manufacturing a car. How many chassis you will produce? At what speed this whole car will not be overturned if suddenly the brake is applied? Then you have to go to software, design everything, test this one, so many iterations you do, and then ultimately you come to, yes, this should be the weight of the car, including everything. Then multi-chip to single chip. You do not know today, but we have seen multi-chip to single chip. There are a number of chips. one chip output is connected to another chip, and then packaged together. Only thing, the input control and the output pins are available here. That is what is the connection inside it. You package yourself. Locally you have packaged it. That is what is the multi-chip. Then all aspects are computerized, whether it is production, whether it is design, all aspects are, because of the complexity, because of the fund crunch. So concept of engineering, when we talk about the concept of engineering, remains the same, but the modes of application changes. Say electronic filter. You know electronic filter. Somebody must be from the electronic branch here. Electronic filter. It remains the same. Whether it is T-type, whether it is pi-type, whether it is M-derived filter, everything, whatever you take, it remains the same. Only thing what it changed. It changed modes and applications. Whether it was electronic filter, a passive electronic filter, or an active filter. So here, mode of electronic, passive to active. Passive, what we used in our days, we didn't have active filter, only passive filter. Bulky inductor, very large capacitor we used to use. That is passive. Very large dissipation of power, loss of signal, everything is there. But the philosophy is same, filtering philosophy is same. Only thing what we have done, we have changed from passive to active using operational amplifier. It became very handy, very cheap, takes very small space. That is what it changed from passive to active. Then finally it came to digital filter, IIR, FIR, finite impulse response, infinite impulse response filter. Now, having said so, we said to appreciate the effectiveness of mathematical modeling, what we must, how do we appreciate mathematical modeling? A, we must display some connectivity. We must tell you what is the connectivity or dependency of engineering on math and modeling. My concept of engineering is, if I know very good mathematics, if I know modeling, I am engineer. My concept. If I know modeling of device, modeling of circuit, modeling of system, anything I know, I am complete. Good mathematics and modeling. But from our scenario, this modeling is not present in your syllabi. In BTech syllabi, nowhere modeling is there. And complete engineering is only both modeling and mathematics, very good mathematics. When I am advocating good mathematician, what is the meaning of this? What does it do? Mathematics. Math helps to form the idea. Analyze what the information is there, analyze it. And then optimize it. That is what is mathematics. If you have good knowledge of mathematics, you can form very good imagination. Then math enhances ability to engage in what? Abstract thinking, and it erases imagination. Mathematical model, mathematical equation is there. what you can do. That's what I was telling. I enjoy playing with this mathematics. Meaning is this, go on imagining. This equation, what can it do? What more it can do? Go on imagine. That is what it is. So again, I reiterate, engineers are innovative and creative. What is creativity? Creativity comes from good imagination and abstract thinking. You must be creative. Having mathematics, very good knowledge of mathematics. Creativity automatically. Then, innovative engineer must be equipped with very good, substantial knowledge of math. So, having said so, I am going to define this like a study of a process or an object in one environment. If it is duplicated in another environment, then it's again what have we done? Any process or any object you study in one environment, and if the same is duplicated in another environment, your model works back. I took this, a real picture. What it showed? It shows there is a cloud, then mountain having brownish color, then having trees. Now if I model it in, I cannot show, the model cannot work. The one. So we must be able to refine it continuously. There is mathematical description. How do you describe this mathematics? Whether partial differential equation or differential complete differential equation. How do you define it? Go on defining depending upon your vision. Numerical analysis, go on changing. Rangaputta method, I use very long way. Now you don't use. There are a number of methods available here, a number of tools are available here, you can do it otherwise. Computer aided design can be said. Thus, modeling is the only effective approach to respond to the current need. What is current need? Current need is crunch of funds, crunch of a space, crunch of time. How fast we can predict the behavior of the system, we can predict the behavior of the device. Alright? And everything, whether we structure, automobiles, graph, diagram, scattered plots, tree. Tree, you understand what is a tree? You are lost in a forest. Tree diagram tells you where you can go. And then the mathematical modeling within this, the mathematical modeling that you can reach there at this place. Then we said the model provides an insight into the physical system. When we devise a model, what it tells you? Device model, this is a device model, a small device model is there. It tells you, it goes inside into the device and tells you what is the behavior of the device, physical behavior of the device. Then different types of methods you can apply to find out finite difference method, boundary problem, or finite volume problem. All these things, that depends upon your experience, which one you apply, where you apply. These methods involve, so when we talk about these methods cannot be for the whole system. You have to split, say, if anybody is here sitting from the background of electronics, even the characteristics of a diode, it can't write one equation. It is split into number of elements. Whole number of elements. That defines that this is the prediction of the behavior. This element, how it is predicting the behavior. Now this one, when we say mathematical modeling, all are under two categories known as black box and white box. What is the meaning of the black box is? You don't know anything. What is inside it? Nothing known to me. No parameter is known to me. I don't have any information about the system, what it is. I don't have anything known to me. That is complete blind. White box? Priori known to me. Yes, I know some priori. Many things is known to me. Then we say it is a white box or a clear box. But practically all are between these two. White box and none falls in this one, none falls in this one. It is practically in between these two. White box and black box. Mathematical modeling may assume different forms of, depending upon the particular system, a system. It can be different. How do you take this? What are the parameters you have assumed? She has not assumed these parameters. Her mathematical modeling will be different than your mathematical modeling. There may be several different types of model of a device or any system. One may be very simple than the other. Other may be more accurate than the previous one. Another may be modeling DC voltage, DC current. Other may be model with AC voltage, AC currents. So model is entirely dependent upon your choice, which way you want to treat it. For example, an optical control model, which one is best? A, nothing but if you want to state a space analysis will be the best one. Transient response. Best one is transfer function model. For transient response, transfer function model is the easiest one. So that depends upon your experience, which model you are going to apply, when, that depends upon you. With that, these things may be described in terms of differential equation. These differential equations may not have exact solution. We have described it, but these differential equations may not have exact solution. Then what do you do? Approximate. Go again back. Approximate. For example, we say, how do you do it? Newton's law of mechanical system or Kirchhoff's law. One is electrical, another one is. Anyone you can apply. That is known as simulation. You can apply it. And then a reasonable mathematical model is most important part of the entire analysis. Whatever analysis you are doing, you cannot say your analysis with the other model will be alright. No. It's wrong way. Your approach is something different. Whatever parameter you assume, those parameters you are feeding into the analysis, those will give you different result than hard model and hard analysis. This only have shown. What do they say? Linear time invariant. What is this? Ain't nothing but transfer function model. How do you do it? Take the Laplace transform. Simple Laplace transform. Say differential equation of y the output, x the input, and we take in the form of the Laplace transform. This gives you simplest equation. Simplified form of the models. One is known as material model. Material model we see here. Material, what is meaning of the material? A scale down there. Wind tunnel. What is the wind tunnel? To analyze the thrust of the rocket. Very long and huge cross section. Wind tunnel you have to construct and then see here. Because physically you can't see in the case of the rocket. So you have to generate here, simulate here, that is what is the material model. Then we said mathematical model. Mathematical model you understand, we put in the form of the equations, symbols. Then we said logical model. Logical model, say if anybody has played with the microprocessor or microcontroller, the harmonium, unless you synthesize sa, the ray doesn't mean anything, sa re gamma. Even you try it, otherwise you will get nothing, no result to you. So that is why the logical. It depends upon this logic. Say this plug pudding is the negatively charged are distributed over in form positive charge. Looking like plums are raising on the pudding. Means uniformly distributed positive charge and negative charge. It's not a complete one solid, but it has equal distribution of positive and negative charges. Then Rutherford came. What he said? Now divided into two parts. One is nucleus.
Excuse me, just a small announcement that after this lecture we will have one more expert lecture and then we will have lunch. Okay, so please bear with us for 10 minutes more. We will have one more lecture, then we will have lunch. Okay?
How much time? Go ahead, no? So how much time? You tell me, Mark. How much time? I can take that. Okay. So nucleus. Now divide into two parts. Nucleus. What is that? Charge. Dense nucleus. And negative cloud. Electron cloud. That is separated into two parts. One is the nucleus, another one is. Then came the board. Bohr model. What is that? Not only two parts. Electrons are present in the second part, but they are orbiting. They are not stationary, but they are orbiting. That is what the Bohr model says. What Bohr model tells you? Why I have taken this refinement, coming to this point only. This refinement I have taken only to come to the point that I want to model the energy. in different orbits of the atom. Different orbits of the atom. So if you take any one electron here, you can say centrifugal force or centrifugal force. Electrons are at a distance from the nucleus, so it has a potential energy. Rotating, it has a kinetic energy. So total energy, if you take into account and convert it, then it gives you 13.6 over n square. N is the principal quantum number. Now see here, the last orbit gives you maximum energy, E3. Last orbit gives you maximum energy minus 1.5 electron volt. Nearest to the nucleus gives you minimum energy. That means any electron jumping from outer orbit to the inner orbit gives you light of quanta equal to h nu. Alright? Then Schrodinger tells you the refinement is slightly more that it is the cloud. Let's say this one. Can you see here? The cloud is moving. Moving. That means quantum mechanical model. Schrodinger gave you the quantum mechanical model of the atom. Potential well, you analyze with this only. And I have to stop here. Huh? So I should stop here. Right? Are you following anything? If you are not following what it is, finding, transmitting from here to there, why? What for? Are you following anything? Whole thing was how to come to the model. Say energy model. I told you this one, energy model. How did this energy model came? Only thing what we did is nothing but the potential energy, kinetic energy taken together. Then we said any orbit has this much amount of energy. So I can predict from which orbit when the electron jumps, or when you will excite the electron from which orbit it goes to what orbit. This is the energy. Very crude example of mathematics. Verland. Very crude example of mathematics I am telling you. Verland is this. What is it? Integration. Mathematics integration. What is integration? Summation bit by bit is the summation of integration. Integration number bit by bit summation. If you are not interested anything, I will stop here. Please, if you are interested then only. Otherwise, what is the fun? Another lecture is there. You go for that lecture. Yes, right. Stop it. How does it matter? To me, how does it matter, man? Could you get anything? You are not getting anything? Could you get anything? Please tell me. Would you get anything? So, what is what I wanted to explain? Anything which you know how to put in the form of model. That's all. In no distance, RC circuit. This RC circuit is there, but the capacitor is there. At high frequency, what will happen to the capacitor? Very high frequency. What is the capacitor behavior? Tell me. Short circuit. At high frequency, 1 by j omega c. Omega is twice pi f. If the frequency is very high, 1 by infinity is 0. So at high frequency, output is 0. Low frequency, it is open circuit. So what is this? This is
Thank you so much, sir. Again, I would like to request Mr. Krishna Kumar Singh sir to give a floral welcome to K.R. Biyani sir. Thank you so much, sir. Now, this is my great pleasure to introduce our next respected honorary personality, who is Dr. Ravi Saini sir, the scientist and CISRN Siripilani. Sir, you have done your PhD from CSIR Siripilani, accomplished your instrumentation engineering from Punjab University, you did your MSc in electronics from Indore, you did your BSc in electronics from Kurukshetra University, you had the standard of senior research fellow in IC design through CSIR Siripilani. So sir, and your research interests are SDLS and VLSI. So this would be our honor to listen your words. So please come upon the stage and share your prestigious words with us.
Hello, good afternoon to all of you. So, I'll try to complete my lecture within 5 or 10 minutes, so please cooperate with me. Okay. So, first of all, I would like to thank the organizer of this conference for inviting me here. So, my topic for this talk is application specific instruction set processor, also called ASIC. Its design methodology and design issues. This approach, which is comparatively a new approach to realize a processor or programmable processor for a targeted application domain, can deliver huge performance and power benefits while regaining the advantage of flexibility or through software programmability. So this is a new approach. So before going to this approach, we will discuss or we will see the alternate approaches that are available for the designer to implement a logic. Then I will briefly discuss about ASIC approach, ASIC design methodology that we have used to design this ASIC. Then we will see the design steps that we follow to design the ASIC, complete ASIC right from the scratch, and then we implemented this ASIC onto the FPGA. Okay, before going for the ASIC implementation. Then we compare this design ASIC with a general purpose kind of processor. Okay. We do the performance comparison, and finally I will conclude my talk. So the first approach that is available to a designer is an ASIC approach. This is very simplest approach. So in this approach, what we will do, we will simply map the algorithm directly onto the hardware. हम डायरेक्ट एल्गोरिथम या फंक्शनैलिटी होती है, ठीक है, दैट विल इंप्लीमेंट दिस फंक्शनैलिटी डायरेक्टली ऑन टू द हार्डवेयर. सो दिस इज द सिंपलेस्ट अप्रोच. दिस अप्रोच विल गिव हाईएस्ट परफॉर्मेंस. ओके, सबसे ज्यादा परफॉर्मेंस यही अप्रोच देती है जिसमें हम डायरेक्टली हार्डवेयर में इंप्लीमेंट करते हैं. एंड आल्सो द पावर डिस्ट्रीब्यूशन वुड बी लेस इन दिस अप्रोच. सो दीज आर द एडवांटेजेस ऑफ दिस अप्रोच. बट द डिसएडवांटेज विद दिस अप्रोच इज दैट इट विल नॉट प्रोवाइड एनी फ्लेक्सिबिलिटी. Now, what do you mean by flexibility? Flexibility means, suppose your application or your functionality changes, okay, then you have to redesign your hardware, okay, or you have to redesign your ASIC. अगर आपका एप्लीकेशन या फंक्शनैलिटी आगे चेंज होता है, ठीक है, तो आपको हार्डवेयर दोबारा से डिजाइन करना पड़ेगा। उस हार्डवेयर को जो पहले डिजाइन किया था उसको फेंकना पड़ेगा एंड यू हैव टू रीडिजाइन योर हार्डवेयर। सो दिस इज द डिसएडवांटेज विद दिस अप्रोच। These architectures, they can be combinational. So I am assuming that you have undergone the digital design course in your degree. सबने पढ़ा है digital design course? उसमें combinational, sequential सब पढ़ा है, right? Article level design, how to do the article level design. I am assuming that you know how a processor works. Processor कैसे काम करता है? सबने C program लिखा है? लिखा है ना? So that C program will be executed by the processor. Okay? Your processor executes that C program in sequence. So that is why they are called sequential languages, because all these statements, they are executed by the processor in sequence. Okay? So there is a sequential processor available underlying the architecture or the BICON architecture, and it will execute all the statements that you write in your C code. This is how this processor works. So the second approach that is available to a designer is a general purpose processor based kind of approach. Okay. So you use processor in your laptop, you use processor in your PC. They are all general purpose processor. Now why they are called general purpose processor? Because they can implement any logic. Okay. You write program. So program is nothing but a sequence of instruction. आप कोई भी प्रोग्राम लिखो, वो प्रोग्राम आपका प्रोसेसर एग्जीक्यूट कर देगा. So that is why this is called general purpose processor. So it can implement any application or it can implement any logic. So it provides full support of programmability. So here you will get maximum degree of flexibility. Okay. But the disadvantage with this approach is that it is very slow. It will not give high performance because speed is very slow. Why? Because this processor doesn't have dedicated hardware functional blocks like ASICs in the execution unit. If, for example, if you want to execute a cosine, if you want to compute a cosine of a number, ठीक है, अगर C में आपको cosine function अगर compute करना है, तो आपको क्या करना पड़ता है? You have to include the math.h header file, right? ये एक्सपोनेंशियल किसी नंबर का निकालना है, then again you have to include this header file. तो इसका क्या मतलब है कि there is no direct hardware support available for all these functions. So there is a subroutine defined in these header files. So you have to execute those subroutines to compute the exponential or sine cosine function. So generally this is slow. ठीक है? ये slow हो जाता है because for example you all know how a processor works. तो सबसे पहले आपका प्रोग्राम मेमोरी में रहता है, ठीक है? So you have to fetch the instruction from the program memory. So you require one memory operation. Then you have to decode that instruction, what that instruction does. Then you have to fetch the operands from the data memory. So this is another memory operation. Then you have to execute, and then this generated result will be again stored back into the data memory. So you require generally 3 memory operations. And these memory operations, they are very slow in hardware. Okay. So they are the bottleneck. Okay. In determining the performance. So for example, if your sine or cosine or exponential function require 100 such instructions, okay, and one instruction will take 3 memory operations. So you require generally 300 memory operations, okay, to execute this instruction. To execute this operation, right? So this general purpose processor based approach is slow in computing the logic, and also they consume a lot of power because all these memory operations they will be done via buses. Okay? Memory से आप fetch करते हो, then the data will go to bus and then again will store the data into the functional unit or it will go into the execution unit. Okay, so the data transfer is via bus. And this bus, they are nothing but they are group of wires. So there is a heavy capacitance associated with these wires, and we all know that power dissipation is directly proportional to the capacitance. जितना ज़्यादा capacitance होगा, उतना ही power dissipation आपका बढ़ेगा. So as a designer, as a VLSI designer, I have to reduce this power dissipation. So I have to reduce this capacitance. ठीक है, तो जितने कम memory operations होंगे, उतना ही कम आपका power dissipation होगा. Now the question is, what should be the application to demonstrate and test this ASIP approach? So we have chosen a parametric speech synthesis that will convert text into speech in real time. Okay, and its public, its C code is available in public domain and it is developed by DX so it is available. So we have taken this C code, because we have taken this application and we have designed the ASIP for this application. Okay. And we have demonstrated that we are getting the speech. The speech is generated in real time. As soon as you hit the text, as soon as you enter the text, the speech would be developed in real time. So this is the design. So I will not go into the details because the time is less. So these are the steps of the ASIP design methodology we have adopted to design this ASIP. So the first step in the design process is the application analysis. Okay. So you can do the application analysis using tools. So अगर आप Unix operating system use करते हो तो there GNU Prof is a tool available to do the profiling. ठीक है, तो GNU Prof tool है. उस tool से आपने जो C code या कोई आपका कोड है, उसको आप उसको दोगे as an input. So it will give the number of functions that is required by that code. It will also give the operations that it uses. Okay, so all those information will be given by that tool. Okay, so you can use GNU Prof as an application tool, application analysis tool. So we have done the application analysis of this C code that is available with us. So I'm not going to the details of all these functions. So these are the functions that are required by this application, and you can see now this speech is processed frame by frame. Okay, just like your video processing. Video processing में भी यही करते हैं, images रहती हैं, and we'll process all those images one by one. तभी तो वीडियो दिखता है. आप 27 फ्रेम रेट्स पर सेकंड में आप करते हो प्रोसेस, तो आपको वीडियो दिखता है, अदरवाइज तो कोई इमेजेस नहीं है सीधा. तो सिमिलरली वी विल डू द स्पीच प्रोसेसिंग फ्रेम बाय फ्रेम. So this LP resonator, this is the second order resonator filter. So you can see in the table that it is the frequently required function. So it is required 960 times in one frame. Okay. Similarly, this natural source, it will compute the natural sourcing output. So it requires 240 number of times. Gen noise, this function computes the average of 12 random numbers. Okay. So again, this function is required 60 times in one frame. Now all these functions, they require operations, arithmetic operations and mathematical library functions. Okay. So here, this table gives the frequency of these operations required by these functions. So this get host, it will take the parameter from the outside, from the host environment, and supply these parameters to the ASIP. So this get host function, it requires 4 addition subtraction operations, and all these operations are floating point addition subtraction operations. They are not fixed point. Okay. So it requires 4 addition subtraction operation, 20 multiply operations, and 3 division, floating point division operations. So in this, so you can see the table here. So all these operations require this much number of operations. Now all these operations that we added, all these operations. So this table shows that this addition subtraction will require 3,417 times to process one frame. Okay. So now the real time constraint to process this one frame is 5 milliseconds. So this 5, we have to process this frame within 5 millisecond time. So it means we have to process 200 frames in 1 second. Okay. So then we have multiplied this addition subtraction operations, and this much number of operations we require per second. So now based on this application analysis, so this step will become the guidance for ASIP instruction. So now based on the application analysis, we will select the instructions. What would be the instruction in the instruction set of this ASIP? ठीक है, तो हमने एप्लीकेशन एनालिसिस कर लिया. ठीक है, अब एप्लीकेशन एनालिसिस करने के बाद हमको थोड़ा आइडिया हो गया कौन-कौन से ऑपरेशंस, कौन-कौन से फंक्शंस हैं जो कि बहुत ज़्यादा बार कॉल हो रहे हैं. ठीक है, those are frequently required by the application. हर कौन सा फंक्शन कितने ऑपरेशंस ले रहा है, ठीक है, वो आइडिया भी मिल गया. तो नाउ आई कैन डिसाइड द इंस्ट्रक्शन सेट ऑफ दिस ASIP. ठीक है, so now I get an idea, see what would be the instructions in the instruction set of this ASIC. So this LP region, so it is frequently required. So I have decided that I will give one instruction, one application specific instruction for this function. Geno is again, this is frequently required by the application. So I give one instruction, specific application specific function for this instruction. Similarly, I require cosine and exponential applications. But this type of instruction, you will not get this type of instruction in a general purpose kind of processors. So these are application specific instructions. Right? Then convert IF, that will convert integer to floating point, and again floating point to integer. We require this type of instructions to execute this code. So we give two instructions for this. We also require rounding kind of operations. So we give one instruction, application specific instruction for round, and we give one instruction for lookup, because we have to convert the decimal values into linear values. So we give one instruction, that is lookup, look underscore f, for this as an instruction, as an application specific instruction. So now I have to decide the clock frequency, at what clock frequency my processor work. मेरे को decide करना पड़ेगा. जैसे for example your Pentium or your Intel processor works at 3 GHz. So what do you mean by that? So इसी तरीके से I have to decide the clock frequency before designing this ASIC. So I have given some clock cycles based on our prior experience to all these functions, to all these operations, and then we counted that to process one parameter we require total 62,675 cycles, total number of cycles. Okay, and we all know that with execution time to compute one frame is 5 milliseconds. So the required clock frequency would be the total number of clock cycles divided by the execution time. So it's come out to be 12.525 megahertz. So now we also require some more cycles to fetch for other operations like input, output, data fetch, data store, instruction fetch cycle. So we have not counted all those cycles here at this stage. So we have decided that we will keep a clock frequency of 25 megahertz for this processor. Now we have the next step is the proposition of data path of the microarchitecture for this ASIC. This is the block diagram of this top level diagram of this ASIC, designed ASIC. This would be the microarchitecture of the complete ASIC. Here you can see all these blocks. They are not simpler blocks. They are dedicated hardware blocks. So all the algorithms and their associated controller, they are embedded on all these blocks. This first block is MP flow. This is a program memory. ISC, it is a block that will compute integer, add, subtract, and then also do the comparison on the two numbers, on two integer numbers. FSC is a floating point addition subtraction block. FMPY is a floating point multiplication. FDV is a floating point division functional block. S cos compute the sine cosine. S exponential do the computation of sine exponential of a number. IJ computes the average of the 12 random numbers. Okay. And all these blocks, they are mini ASICs. They are not simple blocks. Okay. And all these blocks, they are connected with a single bus. Okay. And also they are connected with a control bus, C bus. So this controller will supply all the controls to this block. So we have used it distributed kind of control here in this architecture. So all these so what operation all these blocks have to perform, this will be decided by the controller. So this controller will provide the control signals to all these blocks, and that will be via control bus. Right? And then PCLU for because my PC points to the address of the next instruction to be fetched. PC program counter. Okay, so this block will do the PC related operations like PC incrementing or decrementing. Instruction decoder, it will decode the instruction, and this output of this instruction decoder will be going as an input. It will decide what would be the address of my next micro instruction, or micro instruction or control word. So all my controls, they are stored in a control memory. So generally there are three kinds of implementation available for a control. कंट्रोल को इम्प्लीमेंट करने के लिए तीन तरह के ऑप्शंस रहते हैं. एक होता है आपका हार्डवायर्ड, तुमने पढ़ा है सब बोरिस मैनों में, हार्डवायर्ड अप्रोच, और आल्सो कॉल्ड रैंडम लॉजिक इम्प्लीमेंटेशन. देयर यू इम्प्लीमेंट द कंट्रोल यूजिंग gates or logic gates. The second approach that is available to implement the control is micro-coded approach, where you store all the controls in. So ये जो operations होते हैं, they are called control statements. So here we require jump branching kind of thing. You require branching instructions to execute this kind of operations. ऐसे statements होते हैं. So we also require branching kind of instructions. We also require loop statements. Okay? So loop statements are also there in our application. So we have kept two loop instructions, one to start the loop and one to end the loop. And then we also keep instructions for subroutine call. Okay? So one instruction is required to call the subroutine, and then after executing all the instructions that are there in the subroutine, we have to again return the control back to the program. So we require return statement, return instruction. And we have already seen this application specific. So we have kept 8 application specific instructions that you will not see in a general purpose kind of processors. These are the instruction format we have defined for all the 44 instructions. Example, so this instruction word is a 32-bit instruction. Okay? So this div fc, it will divide one floating point number to a floating point constant. What does this instruction do? It will divide a floating point number that is given by this address given in PTR1 field. Okay? So it will, this address will go to the floating point memory. So it will fetch the operands from the floating point memory, and this number is divided by this constant that is supplied within the instruction. So this instruction will come as an extension word with this instruction. Okay. These first 6 bits, they are the opcode bits. Okay. So we have total 44 instructions, so we require 6 bits to encode all those instructions. ठीक है ना? 32 के लिए 5 चाहिए bits encode करने के लिए. 32 से ज़्यादा चला गया तो we require 6 bits. 44 instruction है. So we require 6 bits to encode. We require 10 bit for data address. We are not using these 3 bits, and then this extension word. So this 32. So we are using IEEE sub 5 for standard for floating point data. So I require 32 bits. Yeah. So this constant is coming as an extension word to the instruction. So in this way we are encoding this opcode. So we have kept 00 for arithmetic, 01 for data move instruction, 10 for program control instruction, and 11 for application specific. So this is div. So this comes under the category of arithmetic. So we have assigned 00. Okay, here 11 means we have defined 4 categories for all the instruction. One is when we have to do the operation integer. Okay, when both the operands are integer, then we encode 00. Okay, when one is integer, other is constant, then we encode 01. And when one is floating point, when both the data are floating point, then it is 10. And if one is floating point and another is floating point constant, then it is 11. So here this is 11. Okay, for category. And for member operand, again 11. So in this way we have encoded all the opcodes or defined all the instruction bit width. This is an example of branch. So now the next step is to implement the control part. Okay. So for control part implementation, we have used the hardware flowchart methodology. So this is a very powerful technique used at the RTL level, register transfer level. सबने पढ़ा है इसमें register transfer level. So at that level we have to capture the register transfers. आपके जनरली प्रोसेसर या कोई भी synchronous digital system हो, उसमें होता क्या है? We have to take data from one register. We have to do the combinational processing, and then again we have to store the result back into a register. So this is one register transfer. Okay? Register RTL level डिजाइन में क्या होता है? Register transfers ही होते हैं. ठीक है? तो कोई भी सिस्टम हो, ठीक है? Any digital system, any synchronous digital systems, we have to capture these register transfers at the RTL level, register transfer level. ठीक है? So this hardware flowchart methodology, this is a very powerful tool used at the RTL level. So to capture the RTL level activities on a clock by clock basis, on a step by step basis. तो जैसे आपने FSM पढ़ा है, फाइनल स्टेट मशीन मिली हुई पढ़ा ना, तो there आप स्टेट मशीन यूज करते हो. So that state, we have to capture that state using hardware flowchart methodology. We will see by taking an example. So this is, we're not going to the detail. This is how a flowchart looks. Okay. So here you define your register transfers operation for task. Here. Then you define the access type, whether you are reading from the memory, you are doing the writing to the memory. So you can define data read, DR, DS, or IR, whether you are reading from the instruction or fetching the next instruction from the program memory. Operation time, whether you are performing addition operation or multiplication operation. So here in this field you can define this part here. So this will give the next state transition. The next, how you are accessing the next micro instruction from the control memory. So here, if you are accessing the micro instruction next, then it is called DB, direct branch. Okay. If you are fetching the next micro instruction, then this is DB. Okay. So you can define DB here. If your micro instruction, if your address of your micro instruction comes from the instruction itself, then it is called IB. So here you can specify whether it is DB or IB. This state ID will tell me my present state. Okay, this type, this state ID. Okay. So this will give me my present state, and this next state would tell what would be my next state. Okay. So after completing this state, where I will go. So this next state ID will give me the next state. So before writing the hardware flowchart methodology, we have to define the rules of operation. Okay, so I'm not going to do the details. So we have defined the rules of operation. Okay, so these are the rules of operation we have defined. Now we'll see an example of an exponential instruction. So this is the opcode for the exponential instruction. This the operand address will be given by the source PTR2. Okay, and then the result will be stored at this destination PTR1 field. So this address will be given by this 10-bit field. Okay, where you have to store the result. So these are the hardware flowchart we have written for exponential function. First, this PTR1 field of IR will go to the PTR1 range. So first of all, you have to store the destination address in the PTR1 range. Okay, and this PTR2 field where you have to fetch the operands, this will go to the floating point memory because this data is available in the floating point memory. So it will go as an address to this floating point memory. Okay, to fetch the operands. Then this, so it will take one state, okay, or one clock cycle. So at the RTL level, every designer has to ensure that all these register transfers will be done in one clock cycle or in one state. एक clock cycle, एक state या एक step सब कुछ एक ही चीज होती है, ठीक है? एक स्टेट में, ठीक है, हम क्या काम करते हैं, जितने भी ऑपरेशन करते हैं एक साइकिल में करते हैं, ठीक है? तो वही हमको कैप्चर करना है यहाँ पे, all the register transfers, ठीक है? Then the result of this floating point memory जो हमने डाटा एक्सेस किया है, that is available in this register, it will go to the F2IS block. ठीक है? तो जो हमारा ब्लॉक है exponential function का, it is not a floating point exponential block. So first of all, you have to convert this floating point data into special format, which is a 25-bit format. ठीक है? So we require one special block to convert this. So first it will go to the this data will go to this block via bus. Okay. So again, it requires one state. So here, so this block F2IS will need it needs one clock cycle to compute its result. So this state is free. So in this state, what I am doing? I am doing the PC incrementing because this state is free. So I can do this operation task here. Okay. Then now the result of this F2IS block is available. Now this register, R0 register F2IS, it will contain the output of this F2IS block. So it will be gone. So it will be going to the input register of the exponential block. और ये exponential block exponential compute करेगा. So we have to load this data to the input register of this exponential block. Now this exponential block will take 54 clock cycles to compute the result. इसको 54 cycles लगेंगे. ठीक है, कंप्यूट करने के लिए. So the next state, so अब प्रोसेसर को वेट करना पड़ेगा 54 क्लॉक साइकिल के लिए. ठीक है, तो जब आपने लोड कर दिया तो then this processor goes into the wait state. Now it is waiting for the result to come. ठीक है, so ये जो wait count है, it is from program memory. So in this way we have encoded all the control fields, all the 15 So 17 control fields. And now we have to derive the control words from the hardware flowcharts. So we have to design the micro instructions. So here, so this is the first state of a add II instruction. So this PTR1 field of IR, it will go to the PTR1 fetch. Okay. So this is my first operation. So the first operation is PC increment. So I have defined 001 for PC instruction, PC increment. For integer memory, I'll encode this control as 01. Okay. For data rate, I'll encode as 00. Okay. So according, by seeing all the operations, by seeing all the register transfers, I'm deriving the controls from the hardware flowchart. So we have derived the controls for all the states. Okay. So these are the 5 micro instructions required by this add II instruction. Okay. So in this way we have derived the controls. Okay. Finally, I'll conclude. These are the functional blocks, architecture of the functional block that we have designed. I'll not go to the detail. These are the synthesis results. So we have implemented all these blocks on the FPGA. So these are the results, synthesized results. Then we have done the testing. I'll not go into the philosophy of how we have done the testing of these functional blocks. Then how this is the input interface protocol that we have designed. This would be the timing diagram. So this is the handshaking protocol. Okay. This is the controller that we have designed for output controller block. So this is the approach that we have used for integration of the full ASIC. This is the overall synthesis results of the complete ASIC on the FPGAs. Now this is the performance comparison. Now we have to prove that the approach or the methodology that we have adopted is better than the other approaches. So we have compared our ASIC with a general purpose kind of processor. So we have taken Leon 3 processor. So we can see here that this cycle count to compute this ASIC is only 82,000. And this Leon 3 is taking 7 lakh clock cycles to compute this, to realize this application. And power, so it is the power dissipation is only 28 milliwatts in case of ASIC. But here it will dissipate 1 watt of power if you are executing this application onto a Leon 3 processor. So we have seen that this approach, the methodology or the approach that we have taken is giving me the higher performance, and also my power distribution is as low as possible as compared to other general purpose processors. Conclusion. Thanks. Sorry, I am open for the questions. Sorry, I have taken too much time. So मैंने तो सब कुछ students के काम आ जाएगा. So if you have any question, you can ask. Because to understand all those things, you have to undergo a computer architecture course. Computer architecture आना चाहिए. You know SDLs like Verilog और VHDL एक आनी चाहिए. ठीक है. आपको डिजिटल डिजाइन वाला कोर्स भी आना चाहिए. ठीक है. आप you have to आपको VLSI डिजाइन स्टेप्स या VLSI डिजाइन मेथोडोलॉजीज भी आना चाहिए. कि सारे स्टेप्स या सारे कोर्सेज करने के बाद ही आपको चीजें समझ में आएंगी. अदरवाइज समझ में नहीं आएंगी.
All these designs that you have shown, the ASIC, is it a microprocessor or not? Is it a microprocessor kind of?
This is an application specific processor. You have designed this processor right from the scratch. We have designed all the instructions. We have designed the micro architecture for this processor.
So the architecture, like if I have a Pentium chip,
yes,
that architecture will be similar to this, or that
no,
kind of a different architecture?
They use different architecture. They use this architecture.
So this is like a
so here you can't pipeline this architecture. This is not a pipeline architecture.
Right.
There you use this pipeline architectures because here most of the instructions they'll take more than 1 clock cycle. So I can't pipeline because they are taking variable number of clock cycles. So my pipeline नहीं बना सकता इस architecture. and there all the instructions will take equal number of clock cycles.
So this is basically a microprocessor you want to design.
Yes, for a particular application. So if you want to improve the performance of a particular application, so this would be the better approach. That's what we have tried to achieve, or try to show. Yes, any other question?
Sir, passive approach is the operated approach of passive approach.
Yeah, pardon?
Sir, passive approach is the operated approach of passive approach.
क्वेश्चन क्या है कि एसिक अप्रोच का अपग्रेडेड अप्रोच है, ये करें?
What is the basic difference between ASIC approach and ASIC approach?
एसिक एंड एसिक. एसिक मैंने बताया ना स्टार्टिंग में कि एसिक के अंदर वी आर प्रोवाइडिंग इंस्ट्रक्शंस to provide the support for programmability. In ASIC, you do not have support of instructions, so you can't, you do not program ASIC. So there is no flexibility in ASIC. So ASIC is आपका एल्गोरिथम उसको डायरेक्ट आपने हार्डवेयर पे इंप्लीमेंट किया, आपने कोई इंस्ट्रक्शन प्रोवाइड नहीं की, कोई प्रोग्रामेबिलिटी नहीं है. ASIC approach, we are using the ASIC approach in the functional blocks that are there in the execution unit. तो वहाँ पे हम वो अप्रोच यूज कर रहे हैं डेडिकेटेड वाली. But we are also providing instruction support to support programmability. कि अगर बाद में आपका एप्लीकेशन चेंज भी होता है तो आपको सिर्फ प्रोग्राम में चेंज करना है, हार्डवेयर में चेंज नहीं करना है. So your instruction will be decoupled to the hardware. इंस्ट्रक्शन आपका यहाँ पे है, हार्डवेयर यहाँ पे है. तो अगर आपका एप्लीकेशन में कुछ चेंज भी होता है तो आपने ये इंस्ट्रक्शंस यूज किया है अपने एप्लीकेशन को रियलाइज करने के लिए, तो आपको प्रोग्राम में चेंज करना है, हार्डवेयर में चेंज नहीं करना. तो ये वाली एसिक के अंदर ये फ्लेक्सिबिलिटी नहीं होती. एसिक में अगर आपका एप्लीकेशन चेंज होता है तो आपको अगेन यू हैव टू रीडिजाइन द हार्डवेयर, दोबारा से हार्डवेयर डिजाइन करना पड़ता है. सो देयर इज नो फ्लेक्सिबिलिटी. बट इन एसिक यू हैव द फ्लेक्सिबिलिटी, क्योंकि हमने इंस्ट्रक्शंस प्रोवाइड कर दिया है, हमने हार्डवेयर को डीकपल कर दिया है, ठीक है, विद इंस्ट्रक्शन सेट. तो अब आप इंस्ट्रक्शन सेट को यूज करके अपना एप्लीकेशन रियलाइज कर रहे हो, जैसे आप सी में करते हैं. आप सी में प्रोग्राम लिखते हो, ठीक है, तो अगर आपका एप्लीकेशन चेंज भी होता है तो आप सी में चेंजेस करते हो. मॉडिफाई योर प्रोग्राम को मॉडिफाई कर लो. आप हार्डवेयर तो चेंज करते नहीं हो, क्योंकि सेम सीपीयू रहता है, सेम पीसी रहता है, उसको चेंज थोड़ी करते हो, हार्डवेयर चेंज थोड़ी होता है. तो सिमिलरली हियर आल्सो योर एप्लीकेशन यू हैव टू डू द चेंजेस इन योर एप्लीकेशन और इन द प्रोग्राम, योर हार्डवेयर रिमेंस द सेम. तो ये मिल जाता है एसिक अप्रोच.
Well, thanks to both the speakers, Professor K.P. Singh and Dr. Ravi Seni. While Professor K.P. Singh started the miniaturization, explaining the modeling, and then advocated how vacuum tube reduced to transistor. While miniaturization was on, hardly anything I could have done as chairman in miniaturization. Anyway, and thanks to both the speakers for informative and technical sessions. Thank you. I hope you all must have enjoyed. Thank you.
Now, after receiving such significant knowledge, we have with us young scholar Ms. Gargi Punia, who wants to share some words of her. Now, I would like to request Professor Dinesh Pidda sir to proceed the questionnaire round for this session as a chairperson.
outlines overview of microstrip antenna, feeding methods of microstrip antenna, characteristics of basic patch microstrip antennas, my design and the simulation result, conclusion and references. I am using this microstrip patch antenna for microwave frequencies, and microwave frequencies are greater than 1 gigahertz. It is usually consists of a metal patch on a dielectric substrate, and the other side it has a ground plane. The patch may be in a variety of shapes, but rectangular and circular are most common. The variety of shapes are, we can use rectangular, square shape, circular, annular ring, triangular and elliptical shape as a patch on the microstrip patch antenna. Advantages of microstrip antenna. These are the low profile antenna, easy to fabricate, easy to feed, easy to use in an array. Patterns are somewhat hemispherical with our moderate directivity. Disadvantages of microstrip antenna. It has low bandwidth, efficiency may be lower than with other antennas. If we compare Yagi-Uda antenna with microstrip antenna, then this antenna has lower efficiency. Efficiency is limited by conductor and dielectric losses, and we can consider the surface wave losses also. We cannot handle extremely large amount of power due to dielectric breakdown. Applications of microstrip antenna. We can use microstrip antenna as a satellite communication, microwave communication, cell phone communication and GPS antenna. Feeding methods. We are using feeding for connecting our source to antenna. We have 4 different feeding methods for a microstrip patch antenna. One is coaxial feed. In this we connect a coaxial cable with the patch, and in this process the lower layer shows the ground plane, H shows the thickness of the dielectric material, epsilon are the permittivity of dielectric material, and the upper layer shows the patch, and the coaxial cable are connected at the midpoint of the patch. Advantages of coaxial feed. It is simple, directivity is compatible with directly compatible with coaxial cables, easy to obtain input matches by adjusting feed position. You can change the feed position and easy to obtain input match. Disadvantages. Significant probe feed radiation for thicker substrate. If we use a thick layer of substrate, then the radiation by the probe occurs. So this is the main disadvantage of coaxial feed. It is not easily compatible with arrays. If we design arrays, then it is not compatible because we are not connecting more than one coaxial cable with the patches. So we for this purpose we use microstrip patches, microstrip lines for connecting patches with input signals. The other is inside feed. We can also call microstrip feed, and it has advantages of, it is also simple, also for planar feeding. It is used for planar feeding, easy to use with arrays, easy to obtain input matches, and it has a disadvantage. If we use a thicker substrate, then the radiation occurs. For deep matches, patch current and the radiation pattern may shows distortion. The third one is proximity coupled field. It has in this process a ground plane, then a dielectric substrate, then a microstrip line, and then also a dielectric substrate, and then mount a patch on the dielectric substrate. It has advantage allow the planar feeding, less line radiation compared to the microstrip feed, higher bandwidth it is allowed. Disadvantage requires multi-layer fabrications. Alignment is important for input match. Fourth one is gap coupled feed. In this we have a gap between the patch and the microstrip line. It has an advantage. It is also used for the planar feeding, and it can allow for a match even with a higher edge impedance. If we use a high impedance surface, then we use this gap coupled feed. It has also disadvantage requires accurate gap fabrication. We required a accurate gap between the patch and the microstrip line and requires full wave design. Aperture coupled feed. In this process, the lower layer is ground and then dielectric and then a layer of metal, and we have a slot on this layer and then mount a patch, then another layer of dielectric, and then a patch is mounted on that dielectric. It has advantage, allows for planar feeding, feed line radiation is isolated from patch radiation, allows for use of different substrate to optimize antennas, feed, circuit performance. Disadvantages requires multi-layer fabrication. Alignment is important for input match. Now the other part is characteristic. These are the characteristic of normal patch microstrip antenna. In this, the bandwidth is directly proportional to the substrate thickness. The probe inductance become large enough so that matching is difficult. The bandwidth will decreases. The bandwidth and gain is inversely proportional to the dielectric constant. The bandwidth of rectangular page is proportional to the patch width. Proposed design, which I am designing. I am designing a piece type of patch antenna, and I am using a coaxial feed in this design. And after that, I am changing two dielectric substrate. One is FR4 epoxy and second is epoxy Kevlar. FR4 epoxy have permittivity 4.4 and epoxy Kevlar has 3.6. And now I am measuring that gain and radiation pattern and the return losses of due to these material changes. If I am using FR4 substrate, then operating frequency we can also call resonant frequency at this time, and 9.8 gigahertz, and get the return loss minus 21.4158 dB, and the gain is obtained at this frequency is 4.45. This one is shown in next slide. And then I am using the zero angle radiation pattern, and then I have got the magnitude of 4.4564. If I am using epoxy Kevlar, then the resonant frequency or the operating frequency is 10.8 gigahertz, and
the field of electrical engineering.
and one is electrical engineering rather than to be specific. So what is happening around the world in electrical engineering? I will quickly give you a recap of all those what has happened. So as we all know that per capita energy consumption is an indicator of development. So demand of electrical engineering is increasing exponentially, whereas installation of new generation transmission capacity could not grow at the same pace. Because of economic reasons, because of environmental reasons, putting a plant is capital intensive thing. So there is a gap between the demand and supply as usual. To bridge this gap, electrical engineer thought to try many things. Okay, so what was initially the aim? There was a crisis of electricity in 1970 when the petroleum prices hike was there from oil exporting companies. So then people started thinking what to do. So then the thought came that there are 3-4 strategies which we should adopt. Number one, better utilization of existing infrastructure. So whatever you have, try to use it optimal. Number one. Number two, improve technical efficiency of the system. Number three, improve commercial efficiency of the system. These are two different aspects. Commercial efficiency is related to business. Technical efficiency related to your system. So then there was an effort to improve technical efficiency and commercial efficiency both. And for this, they need a shift in paradigm. Total change of thought came into mind. So what to do, how to do. Okay? So let me quickly brief. So then they thought that because we have energy scattered all around the world, initially in the ancient time, we used to put big power plants in remote areas. And they found that energy is available everywhere. In the form of solar energy, in the form of biogas, in the form of wind, everywhere. So then the thought came that why not take every possible source of energy, wherever it is available, put it to the grid. So small tapping of energy started coming into. So then again, initially you were supposed to pump energy in the system from somewhere else. So this design worked like that only, that we are injecting energy from this point. We cannot inject energy from here. But then when you start thinking that take every possible source of energy and put it to the grid, that means you can install a solar plant at your rooftop and you can give this energy back to the system. Now it's reverse. Where you are supposed to take energy, you are pumping the energy back to the system. So this led to definitely a lot of technical drawbacks. As I said, because I cannot go according to slides, there are 45 slides and you are already running out of time. So what is happening around the world? Non-conventional energy sources are being added. Emphasis is on better utilization of existing generation and transmission facilities. As I said to you, rapid and critical changes are taking place around the world. The way electricity used to be generated, transmitted and distributed. There is a total shift. Earlier there was one company which was supposed to be generating electricity, transmitting electricity. We call it vertical structure, where generation, transmission, distribution was owned by one company. Now it's changed, horizontal system. You can have multiple generation company, you can have multiple transmission company, you can have multiple distribution company. So things are changing very fast. So now I will quickly, as I said, I will not go into detail of what is happening. So optimally utilize the available infrastructure. Hengorani, in India, serving in Canada, gave the concept of FACTS, flexible AC transmission system. The ultimate aim was better utilization of existing power and energy infrastructure, controlling power over designated transmission loop. This is very important. You know, according to your Ohm's law, power flows from higher potential to lower potential. Through these technology, you can reverse the flow of power from lower to higher. I mean, this was the beauty of this technology, that you can control the power in desired fashion. So this was the one thing that came into existence around 1987. Idea was to improve the efficiency, better utilization of existing infrastructure in generation, transmission, distribution. This led to development of various FETS devices, flexible acid transmission system devices. Okay, and I will quickly skip this part. So these are the devices that came into existence, and research is still on in the development of these devices, static wire compensator, static synchronous compensator, all these technical things which many of you might not be knowing. But you know, these devices came into existence to improve the usability of existing infrastructure. Okay. Then, as I said, first objective was to improve optimally use the existing infrastructure. Second thing was to improve the technical and commercial efficiency. Then came the restructuring and deregulation. The aim was to, increase competition in the generation sector, transmission sector, and to improve the reliability and efficiency of the system. So, around mid-80s, somewhere around mid-80s, throughout the world, there was a change. The company was split into different companies. Earlier it was one company, Power Electric Utility used to be called. Now it is Gencos, we call it generation company, Transco, we call it transmission companies, Discos and all. Idea was improving technical and commercial efficiency. So this was something on the commercial side. So when they restructured the companies, then definitely they had to restructure the electrical system also. So this all concept this led to the privatization, restructuring, and finally deregulation of power. What is the meaning by deregulation of power? Earlier the power was regulated by this one regulatory authority. Now it's deregulated in limited sense. That means you can also generate power. Earlier it was not the case. Private people could not generate power. Now government has opened up. You can also generate power under certain restrictions. Now government now. So we call it deregulated power. So deregulated environment has initiated reforms in our power sector. Now the important thing is, earlier it was electric company. They used to say, we'll supply you, will not supply you. It was their choice. Now consumer has become the key. Consumer says, I'll not take supply from you, I'll take supply from this firm. So in future what will happen? You may say that I want power from Reliance. Person sitting near to you, you can say, I want power from Tata. And I want power. So ultimately consumer will be the key, and consumer will be selective in taking power from different companies. So we need to design our system. Research area is this. You need to design your power system in such a fashion that you can take power from any electric utility you want. Be it Tata, as I said, this is not present situation. This is what we are visualizing. In future, consumer will be everything. Like you go to market, you buy the shoe of your own choice. I want Woodland, I want Nike, I want this, I want, so you are paying for it and you can buy it. So consumer has become key. So as I said, these are the result of restructuring. That company split it into Gencos, Transcos and Discos. Then the concept of a smart grid came into existence. You all know the word smart grid, smart distribution system. What is this all about? Basically, this is a concept given by USA, and we all follow it. This is intelligent grid. We call it a smart grid because US people call it a smart grid. Energy Independence Security Act of USA gave this concept. What is smart grid? It is nothing but grid along with communication, two-way communication, distributed computer, data transfer from consumer to the company. This overlay is called transform grid. So, I just want that you know what is happening in electrical thing. I don't want to go into the detail of what is inside. So, first thing that came into existence is development of change the consumer consumption pattern. Don't use electric iron right now. I can iron my clothes in the night. Don't use washer. I can wash my clothes in the night because this time energy rate is 20 rupees a unit. So you change your consumption pattern. This is the advantage of smart grid. Number one. Number two, you have smart appliances. In future you will have smart appliances. You know, you are chatting with your friends in some hotel and all of a sudden you can come to know that there is a price reduction in electricity. So you switch on your washer and all that sitting in the hotel from your hotel through internet. It will go wireless, it will switch on your washing machine and other things, and you will use electrical energy at lesser price. Number one. Number two, you can have, on your rooftop, you have some solar panel installed. You know, you are storing that energy. Okay, you have battery system, you are storing that energy. And when you come to know the price of electricity is very high. So you say, okay, supply my electricity to the grid. So you will sell electricity to the grid. This is what they are thinking. And this will happen. This is happening in the US also. So, use of peak shaving technology, including advanced storage technology. What's the meaning by peak shaving? Peak shaving means basically, effectively, you are reducing the peak demand by means of other things like dynamic pricing. You are increasing the price so that people are using less energy. So that is when peak is reaching, so the cost is very high, you will cut down your usage. One way is this. Another way is that when you have this kind of thing, you will buy energy from local sources. So these are the things that is happening around the world, and as I said, I will not take much of your time. This is the future power system, how it will be visualized. Now, so smart grid is nothing but basically is a system which supply to different distribution system, and distribution system are the systems which are connected to you directly. So the thing of concern to you is smart distribution. So major changes are taking place at distribution level, because you know that majority of the reliability issues emerges from distribution system, and therefore we need to concentrate on distribution system. So again, ESA, Energy Independent Security Act 2007 of USA, defines the philosophy of a smart distribution system. What smart distribution should have? These are the. I'll just show you the slide. You note down anything if you do not know. I'll explain you, because to cover up all the things in such a small time, it's not possible. So you see, DER, peak shaving, self-healing, sensing, consumer devices, optimization, highlighting, advanced tool, and command response. Some of the things are related to electrical engineering, and some of the things you all can understand. Resources, you have to optimize your resources. It's simple. Then you have self-healing. If you have any problem in the system should be capable of detecting it, and should be capable of disconnecting and connecting some switches so that the system power is restored. I have multiple feeding to him. Okay? If there is a problem in this route, it will sense, relay will sense that yes, there is a fault. It will cut this feeder and switch on this feeder to him. So this is kind of self-healing. To know the self-healing, you need to have diagnosis system. So you need to have good sensors. So everywhere sensor will be deployed, it will be even at a distribution level, so that you know the health of your system. So these are the things. Consumer devices will be smart. As I said earlier, distributed energy resources and peak shaving DER means putting a lot of renewable small energy sources, every possible source of energy to the grid. Demand response, the pricing should be dynamic. Demand response means changing the usage pattern of the consumer. You have a set pattern of consumption. You get up at 6 in the morning, switch on your geyser and all that. Okay? Now I am electric utility, I just want to change your pattern. So what I'll do, I know that you use electricity at 7 in the morning, I'll say the price is 20 rupees per unit. And if you use the same energy, at 9 I'll charge a tariff of 2 rupees. So you say, okay, fine, why should I switch on my geyser at 7 in the morning? I'll switch on my geyser at 9 in the morning. So this is how demand response means changing the usage pattern of the consumer. Okay? Anyway, so these are the things of a smart distribution system. Presently, penetration of renewable energy, DG, is around 3 to 5%. Okay? And up to 15% you can penetrate energy. You see a lot of energies are available. That energy is environmental friendly, renewable, always available. Solar, wind, everything, they are always available. So you should tap this energy and put it for the benefit of the society. Demand response I have already spoken, self-healing we have discussed, sensing as I said, self-healing is not possible if you don't have sensor. If you have some medical problem, you go to the doctor advises you to take some investigation, go for testing. These are investigations. What are sensors doing? They are investigating the health of the power companies. Consumer devices, as I said, should be smart enough. Consumer devices are well informed by the utility. They have a program pricing chart, tariff. Your device, no, this time the rate is high. I should not switch on the electric iron or washer at this time. So they will be off when the prices are high. So your consumer devices will be smart, optimizing distributed assets. Then there should be an optimization of different resources, solar, wind and all that, okay? So for daytime, your solar should be on. For night time, your wind should be on, like this, okay? So you have to decide, because in the morning, there is change in temperature, so wind speed is very high. In the daytime, wind speed is constant, no wind energy, solar. In the evening, again, there is a drop in temperature, so wind again starts blowing. So these you have to coordinate, so optimize the distribution assets. One conductor is loaded, you know, losses are proportional to I square R, so if current is increased by 2 times, losses increase 4 times. So try to cut down the current here and increase the current somewhere else. So these are we call it optimizing distribution. Then there is islanding. What is the meaning of islanding? Again, this is for all people. What is the meaning of islanding? Now, what you want is like you want a system where the system is big and connected yet independent. I mean, you have a smaller system all around. What we think in electrical system, that we should have our own system, but that system should have a communication with bigger system. So we want a big grid and under this small grid. So that if I have problem in small, then big people can help me. But if big people have problem, I can cut down myself from that big thing. So we call it islanding. Selective islanding. If you have sufficient generation, sufficient load, so you can cut down from the grid when in the case of emergency. And this we call islanding. Okay. Challenges not. I will not go into the detail of this. Now, what are the problems presently? What are the problems in the existing system? Again, these are some technical things. There are a lot of losses. System is unbalanced. One phase we are getting 230 volt, another phase 180, another phase 150. Sometimes in the village, if you go, the voltage is not to the mark. So these are, abnormal condition, and abnormal condition always give rise to losses and poor efficiency of the system. So we need to improve all this. Secondly, the computer power electronics loads are non-linear loads. The system was designed for linear loads. Non-linear loads are increasing losses in transformer and transmission lines. So you need to handle those non-linear loads. Okay. Then reactive power demand, again the power electronic based power devices, they demand machines. They are using machines, they demand high reactive powers we have to control and be able to. So these are the remedies that we should use. Okay. These are the objectives that we can achieve. Again, phase balancing, as I said, is a problem which increases losses. Now, what is the conclusion? The conclusion is more energy efficiency and conservation, optimum utilization of available resources, reliability of power delivery and safety of power, adding more clean and green power to the system. This is what we are planning.
Kishan Kumar Singh sir to pay a token of memento to the Dr. Ravi Saini sir. Now again, I request Mr. Kishan Kumar Singh sir to pay a token of memento to Professor K.R. Niyaji sir.